Okay, let's move on. So any question about the cubic spectral phase? No question? Cubic spectral phase. It's a so-called higher order spectral phase. And you have seen it could be a big trouble if you have some cubic phase, because your pole shape could be seriously distorted. You can have unwanted oscillating tails lasting for a long period of time, right? So it's actually quite important that you can compensate for the higher order spectral phase. If you cannot compensate for the quadratic phase, the price you have to pay could be just a broader pulse duration, but the shape is still okay. But if you cannot compress higher order spectral phase, your pulse shape could be very terrible. Okay, any question?
How can we explain the pi jump?
Okay, good question. Why the red dotted curve has a series of pi phase jumps? Why? What does pi phase jump mean? E to the j pi, right? That is pi phase jump. What is e to the j pi? -1. So actually, these phase jumps implies sign switching from positive to negative or from negative to positive. You will have pi phase jump. Okay. So 如果你把它画出这个现在这是强度跟相位两条 curve 的表示法啊。那你如果去画，比如说 real part、imaginary part， 你应该会在这些点出现所谓的 sign switching， 从正到负，从负到正，啊，它的 phase 的 signature 就是 jump， 而且一定是拍的 jump。那你发现它是对齐的哦，每次跳跃的地方都是 zero intensity， 所以这的确就是假设这边是正，这一点再过来就是负的意思啊。但是因为 intensity 没有负的，一定是正，所以它折上来，但是用一个 pi 的 phase jump 来代表。That's it. OK。
那强度有 phase 是什么？
嗯？
强度那个是 intensity 的强度，那个 phase。
It means when the intensity is 0, your phase could be, say this is 0 phase, this is pi phase. So at this moment, your phase is undetermined, either 0 or pi. If you have an immediate jump, that's the meaning. However, a 0 intensity actually has no meaning about the corresponding phase. 所以这个其实是一个很极限的状态啦，反正它的强度已经是0了，你在复数平面0就打在原点，那你有没有 phase angle 可以定义？没有嘛，你高兴叫它几度都行。所以严格说，那里本来就没有 phase 的 definition。
所以其他地方就是 intensity 不为0的时候会有 phase。
在这个图示嘛，intensity 只要大一点，它对应的 phase 就有唯一的 phase。那意思就是，其实一个瞬间你要定义 phase 也不太有意义。我们必须不断提醒自己 ，What is the meaning of phase? In principle, you need a sinusoidal function to define a phase. The timing of the sinusoid is the phase, right? If you have a single instant, you don't have a sinusoid. You don't have a one cycle. How could you precisely define a phase? It's problematic. 所以很直觉的事，但是有时候你细想，还是有很多模糊的地方。Good. Now we have more questions. How to measure temporal phase or spectral phase? we raise these two questions because in the beginning of lesson 5, when we talk about post-measurement, we mentioned that the mission of post-measurement is measuring the complex fields, either in the time domain or in the frequency domain. And if it's in the frequency domain, since spectral intensity is relatively easy to be measured by a spectrometer, our focus is measuring this one, spectral phase, right? If you can do that, you can know everything. But if it's the time domain, you need not just phi of t, but also I of t. You need to measure both because there is no simple instrument that you can directly measure either temporal intensity or temporal phase. Okay. So certainly the phase curves are key information to be measured. Okay. However, there is no physical phase detector. All the physical detectors are about intensity or energy. 对吧？你有看过一个侦测器直接告诉你 phase 多少吗？通常是把 intensity 的phase 的讯号转成 intensity 的讯号，你才知道 phase。你没办法直接就把 phase 读出来。Okay. So one way to get either temporal phase or spectral phase is by measuring instantaneous frequency or group delay, then performing integration. Okay? What does this mean? For example, this is the formula of instantaneous frequency. The carrier frequency plus first order time derivative of spectral phase, temporal phase, which is instantaneous frequency shift function, right? So if you can measure instantaneous frequency, what can you do? Instantaneous frequency minus omega 0, the carrier frequency constant, then it's equal to time derivative of phi t, then performing integration for both sides of equality. You got phi of t. Okay, so temporal phase is equal to time integration of the difference between instantaneous frequency and carrier frequency. Or the integrand is just the instantaneous frequency shift function. If you can measure it, placing it inside the integrand, after the integration, you've got the temporal phase. 所以这边告诉我们，你要量这个 temporal phase， 你不需要一个 phase meter， 你只需要量它就行。这个看起来是有机会量嘛，我量频率我可能办得到。那你只要把瞬时频率量出来，做积分，你就可以得到 temporal phase. That's one idea. Or the group delay is minus of first order frequency derivative of spectral phase. So you got the similar formula. Spectral phase is minus of integral of group delay. It seems difficult to measure the phase directly, but it seems possible to measure group delay, which is a physical quantity of time. 时间总能量啊，这个是 omega 频率总能量。量完了呢，做积分就可以得到我要的 phase function. Okay. But the next question is how to measure instantaneous frequency. Okay. Remember, we need to measure not just one specific frequency, but a function of frequency. Different observation times, different observed frequency. That's what we need to measure. Okay, so how to do that? Think about you have a signal pulse, A of t. I use a rainbow color to illustrate that it's a chirp pulse. It's an upchirp pulse. So initially, the fringe density is lower, represented by red color. And in the end, you have high fringe density represented by blue or even purple color. So I have a upchirped signal to be measured. Okay. If I can create a gate signal like this, represented by the red curve, 我找到一个 gate 讯号。And I purposely place the center of the gate at tau 1, okay? So the mathematical representation of this gate function is g of t minus tau 1, a shifted version of gate function. Then what can I have? Gate the signal at t equals tau 1, so I got a gated signal, a sub sig, 就是被取样过后的讯号，我叫它 a sub sig, which is proportional to the product between a of t and the g of t minus tau. 就是把这个彩色的讯号跟这个 gate 的讯号乘在一起，就是 gate 完的讯号，所以数学上就是相乘而已。OK。However, what should we do after the gating? You have to think about what instrument you can have in reality. We might have a spectrometer only, okay? So I can actually measure the gated power spectrum. I cannot directly measure the gated signal in the time domain. Remember, we do not have fast oscilloscope. If we have, there is no problem about pulse measurement, right? We don't have fast enough oscilloscope. So we need to perform indirect measurement, like this case. After gating, we use a spectrometer to measure the power spectrum, maybe like this. Okay? And since the tau 1, the gating time is around here. So I use a light blue color to represent the gated power spectrum. 因为它取样的位置这边是浅蓝色嘛，我就用浅蓝色代表做完取样之后的 power spectrum 长什么样子。Okay, but what is the mathematical representation of this gated power spectrum? It's like this. Fourier transform of gated signal in the time domain. So you got the complex spectrum, but we cannot measure the complex spectrum, right? We can only measure the power spectrum. So we only measure the absolute square of this gated signal in the frequency domain. Okay? 所以这个就是这个浅蓝色的 gated power spectrum 的数学表示法，就在这里。Okay? But for the time being, we are only interested in the peak frequency, omega 1. Okay? Sorry. What is the meaning of omega 1? It means after the gating, the entire signal is centered at omega 1, which is roughly the color at tau 1. Right? So we only need the color at tau 1 for the moment. 目前我只需要知道这件事，所以其实我也许也不用记录整个 power spectrum， 我就把 peak 所发生的 frequency 记下来就好了。So we got a relation at time instant tau 1, we roughly had the frequency omega 1. That's it. Is it okay? Then we can scan the position of the gate, right? Say we shifted the gate to the right at instant tau 2, we get a dark blue power spectrum, and the peak frequency is changed to omega 2, higher frequency. So we record tau 2, omega 2 together. Okay? If you scan the delay, eventually you can get this, an orange curve. Horizontal axis is the gated time, say tau 1, tau 2, and etc. Vertical axis is the peak frequency, say omega 1 and omega 2, etc. So point by point, you can draw an orange curve, which is already the instantaneous frequency information, right? 当你做完这件事，这个 curve 是不是已经告诉你瞬时频率了？不同的取样时间，我看到不同的 local frequency. This is instantaneous frequency measurement, right? So according to our picture, after you get the orange curve, what should you do? 我为什么要做这件事？因为做完我可以得到什么 ？Phase, right? Temporal phase or spectral phase? Temporal phase by integration of the orange curve. Okay, so you got temporal phase. So you solve the problem of temporal phase measurement in this way, and it looks like feasible, right? 我们好像做得到啊。我就把我的讯号拿来，我的 gate 扫描，然后拿着 power spectrometer 做了一系列的量测，似乎是做得到的。Okay? But this is a simplified picture because for each power spectral measurement, we only record one number, peak frequency. If we keep the entire spectrum, what do you have? For each gating time, you record not just a number but a function. If you do that, you can have a two-dimensional data set, okay, which is named a spectrogram and represented by this picture. This is delay axis, different gating time. This is frequency axis, different colors. Okay? So the two examples simply mean two slices along the frequency axis. 就是我在掏 one 的时候呢，我记下一个 power spectrum， 我把它画在这里。掏 two 我也画了一个 spectrum， 然后扫描所有的 delay， 我不是画了很多很多的 spectrum。组起来，你是一个3度空间的图啊，把它做投影或者是等高线图，你可以得到一个 two-dimensional data set, a function of two variables. Omega is frequency variable. Delay tau is delay variable. So you got a function of two variables. So it's a three-dimensional representation, and this is a two-dimensional projection. And it's named spectrogram, okay? And with a symbol S sub E, okay? 所以如果你想用上一页的 picture， 这个就好了，拿去积分。如果你想做 frog， 你要这个，不可以只有它 ，OK? Any question? Yes.
In reality, how do we do the equivalent gating?
Microscope interferometer. Just like intensity autocorrelation, right? In intensity autocorrelation, we remember that initially we need an even shorter gate to measure fast signal. But if you do not have even faster gate, why not just gate yourself? 就用 signal pulse 自己来 gate， 所以我们就讨论了 field autocorrelation、intensity autocorrelation， 通通都是什么 Michelson interferometer 去做到的嘛。这里也是一样，我这边暂时画的一个比较细的 gate， 对不对？那实际上这个 gate 也可以是 A of t 自己 ，OK。But in that case, this picture will not work, but this picture can still work. Why this picture does not work? When your gate pulse, the red one, is the same as A of t, the signal pulse. You lose the resolution, right? 当你的 gate 跟它一样宽，你怎么能说我取下来的讯号叫做 local frequency， 什么都包进来了？这个 curve 就出不来。But you can still get spectrogram. So that's the motivation we try to introduce frog measurement, starting with this one. Because if this works, forget about frog. 这个比较简单。但实际上就是你常常没有一个这么细的 gate 可以用嘛，对不对？这就是 Frog 想解决的问题。如果你有那么窄的 gate， 这个就好啦，或者 field cross correlation we have introduced. It works if you have a delta gate, right? Good question. Any other question? Okay, I show you some examples, spectrogram examples. Say you have a chirpless signal represented by the blue curve. So you see the fringe density is roughly constant, no chirp. And we have a chirpless gate represented by the red curve. So after performing the procedures I show you in last slide, you can have a spectrogram like this. Delay axis, frequency axis, the entire spectrogram is pretty symmetric. Okay? Then, if you change your signal pulse to an up-chirped pulse, so you can see the fringe density increases with time, higher and higher with time. You got a spectrogram like this, a tilted one. Okay? And the long axis has positive slope. Why is it reasonable? 为什么一个 up-chirp pulse 会给你长这个样子的 spectrogram？ 知道为什么？ The signature of up-chirp is when your gate, the red one, is higher and higher to the right-hand side. You should observe higher and higher local frequencies. So that means your spectrum should be moved to the upward. 就你在 delay 小的时候，你的 spectral center 在低频；你 delay 大的时候，你的 spectral center 会在高频，你的山峰会往上跑，对不对？所以难怪它整个 spectrogram 会斜掉啊，对不对？你从这边切一条看到的 spectrum 一定是比较低频的，从这边切过去看到的 spectrum 比较高频 ，up chirp. So you have a tilted spectrogram with positive slope. And if your signal pulse is down-chirped, you have a different tilted ellipse as your spectrogram. This time your slope is negative. When delay is larger, you see lower local frequency. Your spectral center is lower, so the entire spectrogram tilted with a negative slope. Okay? So this means the sign and the magnitude of the principal axis slope imply the sign and the magnitude of the pulse chirp. Okay. Pulse chirp is the key information we need to measure. And it seems that without any data processing, just looking at the measured spectrogram, you can know a lot of pulse information. 都不用做什么计算哦，把 data 拿出来看。倾斜的程度就包括往哪边倾斜，正还是负；倾斜的大小就是斜率的绝对值是大还是小，其实已经直接反映出带侧脉冲的 chirp 到底是 up chirp down chirp 是很严重的 chirp 还是一点点的 chirp， 你都可以看出来。OK， 好，严重的 chirp 就是这个斜率会很大。轻微的 chirp 就只有它 tilt 一点点，所以你可以看到很多的 information。Bonus question: What will it look like if the signal is of cubic spectral phase? These three examples are chirpless pulse, up chirp, or linearly chirped pulse. These two are linearly chirped pulse with quadratic spectral phase only. So you have simple pictures. How about this? If you have cubic phase, we just saw the cubic phase, right? 你会看到什么样的 spectrogram?
是 C 吗？
Why is C shape?
不是之前那一页的翻译的话，就是它套图是向上。
哦，就是我前面有一个 page 是 cubic face，right？
所以画一个水平轴的话，会看到。
哎，你有这个 pose， 那它的 spectrogram 会长得像是，哎，
会有两个。
这个吗？
对，然后这两个其实是同样的图案。
Good。
所以你每个去采每一个点的时候，会看到可能会有两个可能的东西。
OK， 所以我用你的话来说就是，如果有 cubic phase， 我一个 delay 会看到两个 frequency， 所以一个 delay 切上去，我应该会看到 double spectral peak。那一点一点扫下来 ，maybe 就是向右开口或向左开口的 C，depending on the sign of gamma parameter, right? Perfect. So your student ID? Thank you. Very good. 很厉害啊，哇。So if you are an experienced experimentalist, you do not need data processing. Just using your eyes, you can directly write down the answer. Yes, if you have a cubic spectral phase, it's no longer spectrogram no longer look like this. It could be of C shape. Okay. But spectrogram is not a scientific item only. We have life experience about spectrogram already. I show you two examples. This is what you might have seen from Windows Media Player. When you play some music, you can see something like this. It will change with time, right? This is spectrogram. It shows you the spectrum of the music at different moments. 不同的时间它一直变形嘛，就是它的 spectrum 一直变。那这个图案本来就在告诉你 spectrogram. Different time instants, you might observe different spectrum. Okay, so it's already spectrogram. Or an even classic example. What's this? This is musical score, invented maybe hundreds of years before. Do you know who invented this system? 不知道，你不用上音乐课啊，音乐课应该会教你。这个怎么来的？啊，原来你们不用上音乐课 ，good。当然很难说是一个人啊，但是改良这个系统的主要贡献者之一应该是巴哈或巴赫，12平均律在这个五线谱里面出现的啊。And the musical score is a manifestation of spectrogram. You see, horizontal axis is time, vertical axis means frequency. So different heights means different frequencies, right? 你越往上跑，那个豆豆出现越高的地方，就是越高音嘛，那就是频率轴。时间轴、频率轴记下来，哎，这个就是 spectrogram. So it's nothing new. It's centuries old notation system, spectrogram. Okay. So you see the scientists are just trying to dig out some ancient inventions. You can learn a lot. Okay.